The goal of this project is to use a LiDAR system to make a 3D scan of an object via point cloud and to eventually make that into a mesh. There's a lot of LiDAR systems out there. A lot of them, like this Velodyne LiDAR, use a spinning puck with a bunch of lasers on it shooting out in every direction. They reflect back into the sensor, and that provides the LiDAR a 3D map of the area. While this is really effective, it's also extremely expensive. For the purposes of this project, we're going to try to get some of the same results, but using a system that costs around $100. The object that's going to be scanned for this project is a statue on the University of Maryland campus. It's an education looking turtle. It's outside the Center for Young Children. This seems like an appropriate target for this project because it's about the right size for the sensor that will be described later. However, later on we found that it actually has some faults. The most obvious fault being that it's near a brick wall, so you can't scan the back of it with an apparatus. But later on you'll see that the color of the statue also plays a role in how effective it was able to be scanned. An inexpensive LiDAR apparatus can be made using geometric range finding. For this apparatus, a laser, shown in red, is spaced a certain distance away from a camera, which field of view is shown in blue. Since the camera and the laser are a fixed distance apart, the location of the laser in the field of view of the camera can be used to determine range geometrically. This illustration shows the perspective as seen through the camera. The yellow plane represents a plane that is getting further away from the sensor from right to left. The red line represents a line laser. The line consists of a series of laser points, each one representing a data point. The blue frame represents the field of view of the camera. A center line can be seen on the camera field. Notice that as the distance of the laser from the apparatus gets further away, indicated from right to left, the distance between that laser and the center line becomes closer. This is used to form a range measurement. Using a simple script, this red line can be tracked and this distance determined. This type of LiDAR is an active form of remote sensing where energy is being transmitted from the source out, reflected back, and then received by the apparatus in order to build a map of the environment. You can also use passive forms of remote sensing in order to build a 3D object. One example of this would be using photogrammetry. That's basically where you're taking a bunch of pictures of an object in order to build a 3D map. In that case, you're not sending out any energy, you're just receiving energy from your environment to gather information about the environment. However, passive or active, any form of sensing your environment without contacting it is a form of remote sensing. The first step to creating this LiDAR system was creating a Python script that could track a certain color. You can see in the stoplight tracking that it's tracking the green dot on the sign. Once this basic tracking is achieved, it's implemented onto a laser system. In this setup, a point laser is attached to a box, which is holding it a specific distance away from a camera. This setup uses a similar script in order to track the location of the laser while the camera is running. This setup works as described in earlier figures, the same way in order to gauge the distance that an object is away from the apparatus. Basic range data was collected from this apparatus. This is then plotted, and as you can see, it turns out that it's pretty accurate to the actual range once the value of the offset between the camera and laser and the offset of the laser angle were adjusted. Once the accuracy of this first prototype sensor was confirmed, I moved on to the design of the final sensor. Designing a new sensor for this project became one of the main aspects of this project. Similar projects have used a standardized sensor, but I wanted to design a new one to overcome some of the problems with the standardized sensor. The standard apparatus is designed to be 3D printed, and for my purposes, I wanted to use less filament as I was to use my own 3D printer for this project. Once constructed, the laser was rotated until it was aligned with the camera, and then the apparatus was calibrated as the first one was.
This is my indoor point cloud setup. So this was run last night, generated some pretty good data, just showing this in the daylight for some clarity. So over here we have a tripod set up, and it's got the apparatus mounted to it through the standard mounting configuration, just some lightweighting modifications. On this we have the battery connected to the Arduino and the Pi. The Arduino is simply powering laser for now, but might power some more stuff later when we get into that.
So after collecting all the point cloud data, it's time to process it. That's done through this Python script. So basically that's taking all the images and plotting points based on the angle. So it takes the image and determines the angle based on the file name. From there, it goes through each image and finds the red laser lines with color picker, and then from that laser line it picks out all the points on that line and will create coordinates for each just using geometry. So we'll run through the simple MATLAB script, and then we get outputs. So we can look at one like this, and this shows where our camera was and where our chair is, and we can get a little more detail if we look at an image like this, and we can really see the detail here. We have the chair.
Alright, so I'm here at my target. So I'm running my Pi through SSH. I'm pointing at it right now, even though you can't see it, through my computer over here.
In order to collect data on this target, the line was swept up in 1 degree increments. As you can see, the black areas of the target were not seen well with the initial pass. In later passes, the exposure was turned up to 15 seconds to resolve this issue. So after my first test of data acquisition at my target, I've moved all my files over my computer and ready to convert them. So we can see here the red dot on the right figure is where we're taking data from, and the blue represents the point cloud of the target. This is supposed to be a turtle holding a textbook. As you can see, a lot of it is missing. So the target was painted mostly black, so I think that's where a lot of our error comes from. You can see the white portions right here is where the turtle is holding a white textbook, so that shows up pretty well. You also see the white background UMD logo in the center here pretty well.
So again, here's a setup. So I marked off on the ground here a few points in white you can see. So this is where I'm collecting data from. So I've got 3 points here. So I know the distances those are away from the statue, and I know the dimensions of the tripod and the mount, so that I can go and piece together these 3 sets of data.
So the other night when it was dark out and there was nice weather, I went out and collected my data. In total, I collected 3 sides, each at 45 degree increments. Unfortunately, my statue is next to a bush and a wall, so I can't get all the sides of it. So with this first test of stitching data together, I used these 3 sides. So in order to stitch the data together, I ran it through the Python code discussed in previous videos, and now I'm stitching it together with this MATLAB code. So basically I'm creating 3 separate matrices, all of which representing a different angle. So I import those, and then for 2 of them I transform them using a transformation matrix like this. So that's dictating the angle that's being transformed about the z-axis and the distance x, y, and z that's being transformed. And then I just kind of played around with that, manually transforming the distances and the angles until the data fit together. What we ultimately get is something that looks like this. So overall, this isn't terrible. We can clearly see this is the turtle statue. When we load it into MeshLab, we can start to apply mesh to it using normals. As you can see, this produces a pretty messy result with a lot of noise. We can clean some of this up by removing a lot of these noisy data points and then exporting the model into Mesh Mixer, where we can smooth it out and make it into a solid body. Finally, this body can be loaded into a slicing program and then 3D printed as it was.